MergeSort. We have seen in the previous section that bubble sort can sort an array of n real numbers in n choose 2 steps. Even in the worst case, it is natural to ask whether we can find a better algorithm that is an algorithm that uses less pairwise comparisons. Even in the worst case, every element needs to get compared to another element at least once throughout any sorting procedure. Otherwise, we will have no information about the size of that element. So we cannot expect to find an algorithm that uses less than n over 2 comparisons. This leaves a rather big gap between the two bounds we currently have, that is, the trivial lower bound n over 2 and the proved upper bound n choose 2. It turns out that the truth is much closer to the lower end. There exist several sorting algorithms that can sort n elements in no more than c times n times log base 2 of n steps for some positive constant c. One of these algorithms is called MergeSort. This is because this algorithm will first split the list of n objects into two parts, which are as equal in size as possible, then sort both parts and then merge the two sorted lists together. Okay, you could say, but how will this algorithm sort those two partial lists? The answer to this is the most self-contained answer possible. MergeSort will sort those two lists by MergeSort again. That is, by splitting each of them into two sublists, sorting each of them by MergeSort, and then merging each pair of ordered lists into an ordered list. In other words, MergeSort is a recursive algorithm that calls onto itself in each step. There is one more detail that we must discuss. How do we merge two sorted lists, say A1 less than A2 less than A3, and so on less than AM, and B1 less than B2 less than B3, and so on less than BK? We can do this efficiently as follows. Compare A1 to B1. If A1 is less than B1, then A1 is the smallest of all m plus k elements at hand, and we can put it to the front of the merged list. Then we can continue with the lists A2 less than A3 less than A4 and so on less than AM, and B1 less than B2 less than B3 and so on less than BK, and repeatedly use the merging procedure we are describing. If A1 is greater than B1, then B1 is the smallest of all m plus k elements at hand, and we can put it to the front of the merged list. Then we can continue with the lists A1 less than A2 less than A3 and so on less than AM, and B2 less than B3 and so on less than BK, and use the same procedure again. Example 17.4. The following shows MergeSort at work on the list 3, 1, 4, 2. 1. Start with the list 3, 1, 4, 2. 2. Split the list into the partial lists 3, 1 and 4, 2. 3. Sort the partial lists to get the sorted partial lists 1, 3 and 2, 4. 4. Merge the partial lists 1, 3 and 2, 4 to get 1, 2, 3, 4. 5. And. In the above example, the procedure worked in a very symmetric way since the number of elements to sort for was a power of 2. This does not have to be the case for MergeSort to work. Example 17.5. The following shows MergeSort at work on the list 421, 5, 6, 3. 1. Start with the list 421, 5, 6, 3. 2. Split the list into the partial lists 421 and 563. 3. Sort the partial lists as follows. A. Split them into the partial lists 42 and 1 and 5, 6 and 3. B. Sort the partial lists to get the sorted lists 2, 4 and 1 and 5, 6 and 3. C. Merge the partial lists 2, 4 and 1 and 5, 6 and 3 to get the sorted lists 1 to 4 and 3, 6, 5. 3, 5, 6, not 3, 6, 5. 4. Merge the sorted partial lists 1 to 4 and 3, 5, 6 to get the sorted list 1, 2, 3, 4, 5, 6, 5, and in pseudocode, MergeSort can be implemented as follows. MergeSort I equals to 1 until n. If 1 is less than n, do m equals to 1 plus n over 2, MergeSort 1m, and then MergeSort m plus 1 and n. Then after that we do the merge of 1 m n and do end. Here merge 1 m n is the sub-algorithm that merges two sorted partial lists. It can be implemented, for instance, by copying the two ordered partial lists into a temporary list so that the original lists are not overwritten, and then by moving the smallest elements still in the two lists into the new sorted list. In a generic programming language, that happens with the following code. Merge of 1 m n. For I starting from 1 to 3 until n, do bi equals to ai, I equals to 1, j equals to n plus 1, k equals to l o. While I is less than equals to m and j is less than equals to n, if bi is less than bj, let ak plus 1 equals to bi plus 1, else let ak plus 1 equals to bj plus 1. Then we do the end. How many comparisons will MergeSort make when it sorts an n-element list? Let m of n denote this number, then m of 1 is equals to 0 and m of 2 is equals to 1. For the general case, we claim that if n is equals to 2k, then m of 2k is equals to 2 times m of k plus 2k minus 1. And when n equals to 2k plus 1, then m of 2k plus 1 is equals to m of k plus m of k plus 1 plus 2k. Both of these formulae are easy to explain. Indeed, the first two terms of the original hand side are the number of comparisons needed to sort the two partial lists, and the last term is the number of comparisons needed to merge the two sorted partial lists. Indeed, after each comparison, we are able to place one element to its right place in the merged sort, so n-1 comparisons will place the first n-1 elements in their right place, which then will force the last element into its right place. Note that 17.1 and 17.2 can be comprised in the formula. M of n is equals to m of the floor functions of n over 2 plus m of the ceiling functions of n over 2 plus n minus 1. These cumbersome divisibility issues suggest that we first try to find an exact formula for m of n in the special case when n is equals to 2 to the t. In that case, set mt equals to m of 2 to the t. Then, this recursive relation translates to mt equals to 2 times mt minus 1 plus 2 to the t, then minus 1. For t which is greater than or equals to 1 and m0 equals to 0. Let m of x equals to the summations of mt times x to the t summing for all t which is greater than or equals to 0 be the ordinary generating function of the sequence mt. Multiplying both sides of 17.4, such a recursive function mt equals to 2 times mt minus 1 plus 2 to the t minus 1 by x to the t and summing over t which is greater than or equals to 1, we get that m of x is equals to 2 times x times m of x plus 2x over 1 minus 2x, then minus x divided by 1 minus x. This implies that m of x is equals to 2x over 1 minus 2x to the square minus x divided by 1 minus x times 1 minus 2x, which is equals to x over 1 minus x times 1 minus 2x to the square, which is equals to 1 over 1 minus 2x to the square plus 1 over 1 minus x, then minus 2 over 1 minus 2x. Therefore, m of t is equals to t minus 1 times 2 to the t plus 1. This means that if n is equals to 2 to the t, then m of n is equals to m of 2 to the t, which is equals to n times log base 2 of n minus 1, then after times n plus 1. If n is not a power of 2, then we can add new objects to the list which are larger than all existing objects until n does become the closest power of 2 that is not smaller than n, that is n1 is equals to 2 to the ceiling floor of log 2. With n as input. We can then sort the new list in n1 times log with base 2 of n1, then minus 1, then after the multiplication plus 1 steps as above. The obtained sorted list will contain the original n elements in the right order at the beginning of the list. Finally, note that n1 is less than 2n and the log base 2 of n1 is less than log base of 2 of n, then plus 1. Therefore, in terms of n, the sorting algorithm will never take more than 1 plus 2n times log base 2 of n comparisons. At this point, we would like to stress that MergeSort is a very significant improvement compared to bubble sort. Indeed, the ratio of the numbers of steps in the two algorithms is not more than gn, which is equals to 1 plus 2n times log base 2 of n divided by n choose 2, which is equals to 1 divided by n choose 2 plus 4 times log base 2 of n, then divided by n minus 1. Therefore, the limitations of gn as n goes to infinity goes to 0. So, for large n, the number of comparisons MergeSort needs is negligible when compared to the number of steps that bubble sort needs.